All right, so some other things that may not pertain to just thermal or the workflow in our case study example that we went through today is before we start our studies in an assembly environment, go ahead and correct any unwanted interferences. The only time that simulation will mesh and solve with interference is if we use a shrink fit contact set. So go ahead and take advantage of the interference detection. You can also use the move component, collision detection, stop at collision option if you're trying to look at if things will collide once a load is applied. Another way to just check and see if your study will run to begin with, if you have a proper amount of contact sets, you can take advantage of the contact set visualization plot that's built into the software, or run a simple test that just have gravity. Just make sure that everything's not flying off, they're staying connected relative to each other, that kind of thing, before you turn the gravity off and use your real design loads. So I mentioned at the beginning of our case study the different element types. So we've got the solid elements, sheet metal, which uses the shell elements, and beam elements, which are primarily used when we do weldment profiles, right? The reason why typically you may see less elements whenever you've got a sheet metal part using sheet metal features, or weldment beam element profiles in simulation. The reason why you would see less is because those elements have the rotation elements for each degree of freedom, whereas solid elements only have translation. So if you think of a beam and I'm putting down a load in the middle of that beam that's fixed at both ends, in a solid environment I need much more beams or elements in there, or calculation points, to look and analyze that bending in the middle of the beam. Whereas if I use weldments to model my CAD geometry and I use beam elements in my simulation study, those elements would be allowed to rotate, so I don't quite need as many. So I get the same results. The solve time is better if you use the shell or beam elements, and of course there's a couple applications where that would apply that we discussed in the training as well. Some other things that you could take advantage of with respect to meshing would be the adaptive meshing techniques. The adaptive mesh, there's two types, H or P adaptive. Those will only apply to solid elements. As you saw me do in the case as well, I always suggest starting off using curvature based, and kind of a rule of thumb, at least for one component, if you're doing an assembly, the maximum element size for that component would be, if it's got a uniform thickness, just half the thickness. That's what I typically start as my element size. You can always use the check geometry tool, use any mesh controls to do a localized mesh like we just did, and as I mentioned, the adaptive meshing. Now, coming back to beams, is a way that you can define that beam to only take an axial load. That's how we define it as a truss. Otherwise, by default, it'll just come in as a beam. The joints can be edited, and those are essentially the calculation points. Beams are pretty straightforward. Most likely they're all going to be bonded anyway, but make sure that if you have truss or an only axial load member, that you define so in the beam definition. Shells, the easiest way to define or take advantage of shell elements is by modeling the part using sheet metal. The second way that we recommend to define shells is by using a mid-surface, or you can manually define the shells by a defined face, right? Keep in mind that you have to contact your shell elements from part to part or body to body using the same face that you define the shell as if you do that define shell by face option. So it's a little bit more work for defining your contacts. You can also take advantage of the shell manager to group by thickness, group by material, a couple other items as well, just to manage the shell definition a little bit easier. With respect to contact sets, if you're using no penetration, I suggest turning on the advanced contact set analysis through your simulation options and using surface to surface or node to surface. Typically, it's kind of hard to get nodes from different components to exactly line up multiple spots, so the no penetration node to node option is probably not your best bet. On contacts, when you're setting them up, I have the larger, more stable object in the bottom, and in the first definition or that property manager in that top box, I'll put the one that is less stiff or more subject to move. The target can generally be meshed a little bit coarser, but again, you still want to keep in mind the idea of convergence, mesh validation, aspect ratio, two elements through the thickness, all the other things that I've kind of already mentioned. Of course, as we saw through this, one of the goals here was to reduce the problem size. Of course, we get results in full 3D if we like. Nice pretty plots, but take advantage of 2D simplification or even the symmetry fixture that I showed you. Again, that's under the advanced fixtures. If you want to include the results of a component but don't actually want, if you don't need the results on a component but want to get a load from it, we can take advantage of the remote mass, remote load, get the inputs but not have to mesh it. So that saves a lot of time as well. Another way to save time would be to take advantage of connectors. Those of you that have Simulation Professional get another added benefit by if you have toolbox components, you have an option to automatically convert those to simulation connectors without having to go and manually define those one by one. You can also load simulation data if you're using 2018 and above to bring in the mesh at the component level to an assembly so you don't have to remesh again at the assembly level. You can also bring in things like loads and fixtures from that component level as well. Got a couple slides here on those connectors that I just mentioned. You can get results for pins if you're trying to size pins, specify whether you've got retaining rings or not without having to mesh it again. That's taking advantage of the connectors. We've got rigid connectors, spring connectors, the pins that I just mentioned. We've got elastic supports, bolts, welds, links, and bearings. Now, if you don't have any type of fixtures, I had brought up previously that the only type or way that we can have an assembly or a multi-body part mesh in simulation and run with interference is by having the shrink fit condition. We go through an exercise using that shrink fit condition to it's an example as if you imagine like an inner race of a bearing going on to a shaft. So we kind of go through that example as part of our training class. But in that, we also go over self-supporting loads where we don't actually have any fixtures, right? Some ways to use that would be either soft springs or inertial release. Now, if you're using inertial release, make sure you do not use that in conjunction with any kind of gravity load, centrifugal, or thermal loads because inertia will be affected by that inertial relief. So your results would not be valid. So just keep that in mind. If you have that scenario, go ahead and use soft springs. But even if you don't have a self-supported load and you're trying to troubleshoot why your study won't solve or why it won't run, its mesh is fine, but it won't solve. If it's not the contacts using contact visualization, it could be something to do with the loads or not enough fixtures. And you could take advantage by go ahead and turn in soft springs or inertia relief on and troubleshoot your study that way. I've got a little bit of information on the solvers. My rule of thumb here is I just leave it on automatic and let the software decide which one it is. And I don't have a lot of issues with that. The different solvers would basically take them out different amounts of RAM. That's the biggest difference between them. And there's information in the manual in the appendix. And I'm sure you can find this documentation on the SolidWorks knowledge base as well. Couple of tips and tricks. I had mentioned a few to try and troubleshoot why a study may not solve. Maybe you don't have adequate fixtures. Maybe you don't have the correct contact set, so components flying off another. The elements, of course, or diving off a material cliff. Sometimes it'll fail, and say the solver failed. It may be going beyond the scope of what the mechanical properties in the material definition allow for. So that's typically something we see in custom materials more. So